Any questions? Yes?
Well, on the top there to the right, there's an arrow pointing left, when it should actually point right, I think. And it will never, like, how would you change that? How would you make it?
Right, so that action is probably wrong, right? What needs to happen is the agent needs to get, for example, to this state and explore. Because right now it believes that the best action is going down. But
I'm thinking of the one on top.
Right, this one, right? So how would it go here and get the chance of understanding that going right might be better? The only way of that happening, of the agent having that experience, is if it's like in this state, and instead of doing the action that it thinks is the best, it tries some other random action, like going to the right. Then if it does go to the right, it is going to get the chance of updating the Q value of this thing.
Yeah, but then that would take a long time to
It might.
yeah.
Exactly. So you're right. You're exactly right. It might take a really long time for the agent to update this. This really depends on how you explore. So this exploration strategies that I mentioned, that you do like 90% of the time the best action, 10% some random one, it has a really difficult time dealing with problems like this, where you converge to like a local minima. That this action, most of the actions are right, but this one is wrong. It might take a really long time for you to figure out that this is incorrect. There are more sophisticated ways of exploring the environment that we're not going to cover here that help with this kind of problem. But you're right. It's like if you go to, like, for example, ICML that happened this year, they had 2 entire workshops on how to explore. It's a really difficult problem. But anyway, so that was one application. This is another one where you have a car. The state here is a vector with, I think, 3 numbers, if I remember this right. So the actions are moving the car to the left, or don't move, or move to the right. And the state of the car is just, I think it's the distance, the distance to the obstacle that is right ahead, and the distance to an obstacle that is 40 degrees to the left or to the right. So it's basically like what the agent is seeing. And it gets a reward whenever it collides with something. So it observes the state, it has those 3 actions that it can select from, picks one of those, and it does get a reward or not. And after 20 minutes of learning, of trying things out, it slowly understands, like it updates the map, like the Q table, meaning like every possible state, how to drive, how to move around. And notice how, like, this is really awesome. I think it's awesome because you never gave the map of the environment to the agent. The agent had no idea about where the obstacles were. It had no idea how the obstacles moved, the shape of the objects. It doesn't know what is the effect of the actions in advance. It was learning just based on these rewards. If you collide, you get a reward, a penalty. And based just on that, it figures out what to do in all the situations. So I think that's pretty cool. This is the Atari game. This is what I'm going to discuss in the second part of this class. So here, this is a way more complicated problem. So what do you guys think is the state of this game? So you could think that, well, the state is the position of the paddle, the position of the ball, and if the ball is moving right or left, or something like that, right? That's the information that you need in order to pick an action. But yeah.
You need the position of the blocks.
Yeah, maybe you need, exactly. Maybe you also need to know where the blocks are, that kind of stuff. Let's suppose for now that that's how they did it. It's not how they did it. They did something way crazier. But that could be one representation for the states. The action would be going left or going right, and the reward could be if the ball goes down here, you're penalized. If you break a block, you get a +1 reward. And the agent learns. It learns something really interesting, actually. Well, now it's not doing something very useful, but eventually it's going to learn. And pay attention to the strategy that the agent learns for, like, getting rewards for breaking the blocks. Okay, nothing very interesting happening yet. Now it's going to do something really creative. I hope it shows. Come on.
Åh, fy fan.
Teraz to się da. That's pretty cool. So we learned that just based on rewards.
Mm.
Okay.
Yeah.
Did they, because I'm pretty sure in the game there are different rewards for the different layers and the top ones are worth more. So did they put that in as well?
Yeah.
Because
so-
that would, then it would really make sense that
Yeah.
it's
Yeah,
going
I
for this
assume
as
they
fast
did.
as possible.
Wouldn't you need the directions of the ball as well?
You do, yes. But as I said, what they actually did is something way more complicated. If you really want to solve this problem like the way that we are discussing here, you're right. We should think, like we should start like schedule a meeting and decide what is relevant. Well, the position of the ball, the direction of the ball, how many layers you have, all that, right? What they did is something more complicated. What they did was they decided that the state was a huge vector with the value of the pixels that are showing up on the screen. So the state is literally an image. The agent has no idea, it's just a bunch of numbers of pixels. The agent has no idea if this pixel here where the ball is, if that pixel is on, it doesn't know that that is a ball that it can control. It's just a number initially. It doesn't understand what's going on. It's just like when babies are born, like images just fly around, they have no idea what's happening. That's exactly what happened here. The agent doesn't know what part of the screen is controlling. It just sees a bunch of pixels. And from those bunch of pixels, it tries different actions, gets rewards. So it learns directly from the images that are showing up on the screen. So how many states exist in this game? If the state is one possible screen. All possible screens that could show up, right? So like, this is color, but imagine that this was just grayscale. And so we have like 255 numbers for this pixel, 255 for this one. And that, I don't remember the resolution of, this is an Atari game, I think it's like 200 by 200, let's say. So you have 200 times 200 pixels, each one with 255 values. That's the number of states, of rows that you would need in your queue table. Times 2 columns, because you have 2 actions. So how would you even start updating that table? You can't. That table has billions of states. And that's where neural nets come in, which is what we're going to see next. If you have huge states like this, you don't need to store those tables explicitly. You can store them implicitly by saving them into a neural net. Right? Okay, let's start here and have a 15-minute break and get back.
They had their own. Yeah, but
Okay, so this was the last example that I presented. There's another one. This is another application of reinforcement learning to playing. Not that. This. I don't know how do you call this game in English? This is like a table with
air
air
hockey.
going out of
Air hockey.
There's a creepy robot, looks like Alien. Learns to play like that, which is pretty cool also. And I think it's gonna show in a few moments what the robot actually sees, what determines the state of the robot. Yeah, that's it. So it's basically the XY coordinates of each one of its hands, where the ball is going to, and the XY coordinates of the opponent's hands. And so this is really old. But it's basically RL, and it learns how to play that. That's pretty cool. So anyway, what we're going to discuss now in the second half of the class is how do we do reinforcement learning where in cases where we cannot store all these Q values in a huge table, because maybe you have too many states and you would have to have like a table with 1 trillion rows. We can't do that. And in that kind of situation, we do what is called value function approximation. So like we have the Q values, right, for each possible state in action. We're not going to store them explicitly in a perfect way in a table, right? We're going to approximate them, and usually we do that by using a neural net. Let me give you an example of what I mean. In the case of discrete states, where the state is I'm either in this xy position or in this xy position or here, but x and y cannot be any arbitrary real numbers, you have like a finite number of states, maybe just a few. Then you can do something like this. This is the classical formulation of Q-learning, which is known as the tabular formulation, because it's a table, right? But then you get, like in memory, you actually get something like this. You have, for each one of the possible states, which are discrete and finite, you have a row, and you have 4 columns, and this is what we store. It's a matrix, right? But what happens if there's a million states? This maze was really small. It had just 12 states. You have a million states, you have a huge table, and even worse, what happens if your states are not discrete? For example, if x could be any coordinate, like any position along this room, so like x could be 0 centimeter, 0.00935, could be anything. So you can't store that in a table, you need something a little bit smarter. Let's take a look at the case where the states are continuous, like you're trying to learn how to control a car like this in a racing game. And let's say that the state of your car is going to be described by 3 variables, the x, y coordinate along the track, and this is the angle of the car, so like the rotation. Well, these are continuous values, right? X, y could be anything, the angle could be anything. So how many rows you would have? An infinite number of rows. Or you could try to discretize these numbers, which is something that people sometimes do, but even then it really doesn't solve the problem. Because let's say you discretize x into 100 bins, y into 100 bins, so there's like 100 values for x, 100 for y, and you discretize the angle into 1 degree increments. So there are 360 possible values for the angle variable. How many states would you have in this case? 100 times 100 times 360, which is like 3.6 million states. So 3.6 million rows times, I don't know how many actions you have, like 4 actions. So it's like 15 million numbers. It's really difficult to update 15 million numbers. You need to play this game many times. And so discretizing the states in case your sensors are continuous is clearly not the right thing to do. You cannot store this. So the idea, instead of doing that, is that we're going to learn separate functions. Instead of just one huge table, we're going to learn separate functions Q for each one of the actions. Here I'm assuming that I have a finite number of actions, like accelerate, brake, turn left, turn right. So few, in this case 4. I will learn a function like this, which is like Q for the action accelerate that takes any state as input. And I'm going to learn a separate action which is Q for the action brake, that you give any state and it tells you how good braking is in that situation. So you learn separate functions like this. So how do we do that? There are many different ways. One of them is using a neural net, and I'm going to talk about that later, but I'm going to start with something a little bit simpler than that. One solution could be something like this, which is like a linear model, which maybe you guys have seen in other situations. So imagine that the state variables are the ones that I just described, x of the car, y, and the angle. And a is one of the actions, like accelerate. So how do you compute, how could you maybe compute the Q value for a given state, and given that I just took the action accelerate? Well, you could just arbitrarily decide that that could be computed by a formula like this, which is just some weight, theta 0, plus some other weight, theta 1 times the value of x, the current x, plus theta 2 times the current y, and theta 3 times the current angle. This is going to give you some number, which you're going to interpret as being the Q value of this state and this action. Where are these theta coming from? Like if you set all the thetas to 0, what would that mean? Well, that means that no matter what the state is, what x, y, and angle values are, because all the thetas are 0, we were always going to predict that the Q value is 0. No matter what the state is, accelerating always gives you a total score of 0, which is wrong. Right? So these thetas are, so how do you come up with the correct values for theta? So there's a variant of the Q-learning algorithm that updates these values of theta so that you end up with a formula, with an equation, such that when you plug the state variables into that formula, you actually get something that resembles the correct Q value, right? The correct in the sense that like the number that would have been stored in a table, but you can't. So you want to at least get something that is similar to what would be in the table. And you do that for each one of the actions. Okay, and so as you can imagine, as you adjust these weights, these theta weights, you get different values for theta, depending on the values of x, y, and z. Okay? Does this representation make sense? I'm not saying yet how to find the right values for theta, but does everybody understand why this is computing one possible value for a q for any arbitrary state given this action accelerate? It's just a formula that I came up with. So what is the first obvious advantage of doing this? Before, if we decided to discretize x, y, and sigma, we would need, as I mentioned, 3.6 million numbers. You would have to learn the value of those 3.6 million entries in a table. And now you need to know, instead of 3.6 million, you need to know the value of theta 0, theta 1, theta 2, theta 3. You need to find 4 numbers. And 4 is much better than 3.6 million. So that's the idea. So in the discrete case, which is what I discussed before, you would have something like this. You have 4 actions and 9 discrete states. So 1, 2, 3, 4, 5, 6, 7, 8, 9, something happened. 4, 5, 6, 7, 8, 9, 10, 11.
I don't think it's counting the end states.
3, 4, 5, 6, 7, 8. Right, so it's not counting this. That's right. What happens if you have a continuous state in this case? So here x now is no longer either 1 or 2 or 3 or 4, and y is no longer either 1 or 2 or 3. It could be any number, any real number in this interval. So you have something like this. The agent state is in any continuous version of this xy in this xy plane. So you actually have an infinite number of states, but you still have just 4 actions. So what you could do is, let's denote the Q value for, well, the sigma doesn't really make sense. Well, we could interpret that this agent now also has an orientation. It's not just a point, it's turned somewhere. So given that the agent is in some x and y in this plane, and it's looking somewhere, so sigma is the angle, what is the Q function for going up? I don't know, but you could design this Q function that looks something like this. So I just added this superscript to denote that the Q function is going to depend on 4 weights, theta 0, theta 1, theta 2, theta 3, and it's just like a weighted average of the state variables x, y, and sigma. If you plug in numbers for theta, you get some real number, which is going to be the Q value, your estimate for the Q value of this state, given that you executed up. And you need to do that for all the other actions too. So you need some way of representing the expected score if you are in this state and you execute action down. So it will look something like this. And for the other actions also. Okay, and notice how these weights are different for each one of the actions. Yeah?
Is that the same 4 thetas you're using in all 4 equations, or?
No.
No.
That's why I have this superscript. Like this is
Oh,
theta
okay.
0, there's an up arrow here, meaning that this is the theta 0 specifically for the Q function associated with the up arrow action. So you have like separate thetas depending on the action that you want to model. But still, how many weights or how many numbers you would need to learn now? You have 4 for each one of the 4 actions. You have 16 numbers instead of 3.6. Which is much better. The question is, how do I learn these weights? I need to find the values here so that when I plug the right thetas, given any state, the thing returns the correct Q value. That's the challenge. So we need these 4 weights. Okay, that's what I just said. So let's compare the 2 settings. And now things should become clearer. So like if you have discrete states, this is the environment. If you have continuous states, this is the environment. In the discrete case, the Q function was just a table with 1 row per state, 1 column per action. Now, if we have continuous states, the Q function is really this summation, this weighted sum of the state variables, just like I showed here. Right, these four. If you have 4 actions, you have 4 of these things. That's what I'm showing here. The update rule in the discrete case was just the Q-learning update equation. It's just written a little bit differently here, but it's just what I showed before. And now the question is, what is the update rule? So like updating Q here means that we update one of the entries in the table. After, like I'm in some state, I execute an action, get a reward, go to the next state, I update one entry. In the continuous case, I'm going to do the same thing. I'm in some state, execute an action, get a reward, go to a next state. What is it that I update? I don't have a table anymore to update.
You update the thetas?
You update the thetas, exactly. You update your weights. Then there's an equation that says that tells you how to update the thetas. I'm not going to explain this because this is not the point of this class, but there is a simple way of updating the thetas. If you see what's happening here, you have like Q of the next state, which also happened in the original, like in the other equation, right? You went to some state S prime, and you had to find what is the best action in the next state. There was like a max. Most of those terms, they end up showing up here. I can discuss this in more details if someone wants to, but that's not really the point of this class. But it's like a very simple update equation for changing the weights so that you get like a better Q function for this thing. And actually, if you look at this for long enough, you realize that this is really close to how the update for real linear regression works if you're doing gradient descent. If you have no idea what I just said, you can just ignore that information. But it's a simple way of updating the weights. Okay. Now, let me just show you before I go into the neural nets part of this class, what is really happening here. What's happening is that we decided that we can't store all these Q values into a table, and instead we're designing these linear models. Like there's a linear combination of the state variables here, weighted by the thetas. There's a linear combination of the state variables here, weighted by different thetas. So we have 4 linear models. And so this is one solution for dealing with continuous states, to use linear models like this. And it sort of works in some cases. And one of the cases where it does work is this little game that is available on the OpenAI Gym platform. This is a game where you have to control this thing that's supposed to be landing on the moon. It has to land here. And think about this, like what is the state in this game? The state is the XY coordinate of the thing, the angle, maybe the angular velocity, and the actions are basically, you can like blow like gas or something like to either the left, right, or down, and based on how it throws gas into different directions, it can fly. And the reward is basically, if you fall outside and you crash, you get a negative reward. And if you land in between the 2 flags, the reward is how centered you are. So you have a huge number of possible states, right? All possible X and Y's. It takes a little while to learn. Doesn't know what to do. I think that's really good after 1 hour of training. It just nails it. So this was solved by using basically this technique that I described. You had the actions were throwing like propellant to the left or to the right or down, so you have 3 actions. And the state, I don't know how many state variables they had, but probably at least 5 continuous values. and they just came up with a linear model for the queue function of each one of those actions, just like I showed. So maybe they had a total of 20 weights or something to update, and they just used that simple weight update route that I mentioned, and it works. But this is challenging enough, but that's not really running. But let's think about more challenging problems. So here we have the x and y coordinate of the agent. We have these four simple ways of representing Q. Right? Everybody understands this? Now, what would happen if we have an Atari game like this? So I don't know. I forget how this is called. I think it's not Breakout. There's a name. I forget the name of the game. But there's like an airplane that you can control. River Raid, I think it's called. So there's the airplane, some enemy ships, like a helicopter, fuel thing that if you shoot here, you get fuel. And this is the river, the blue part. And how would you model this as a reinforcement learning problem? You could design a state representation that includes all the information that is required for picking actions. For example, the x, y of where you are, how far away the nearest enemy is, if there's a fuel, like how much fuel you still have left, if there is fuel in the, so you could come up with all these state variables, right? And you get a huge number of state variables. So you would have a huge number of terms in each one of these linear models. Maybe it will not work very well, but you could maybe work on this for months and get it to work. The more interesting question is, could we just, instead of manually deciding which state features should belong to these functions, could we just decide that the state is actually the screen itself, and we just show the screen to the state is the screen, and based on the screen pixels, the thing decides automatically what to do? That's what CNNs allow us to do. So we don't have to manually come up with a state representation. We just show the screen, and the thing learns. So we have a few options for doing that. What would be the state? So like actions are left and right, for example, in this game. There's also shoot, but considering just these two. So what are the state variables? It could be the ones that I described, x and y, the distance to the enemy, and so on. But if we decide that now we want the state to be pixels, so we don't have to hand design these features, these state variables. Well, now this Q function is going to depend on n pixels, and n is probably 400, because it's 200 by 200 image. So we would have like a thing with 400 terms and 400 weights. It's a lot, it's not very ideal. And the number of states, how many states do we have if we don't use something like this? This is actually an 84 by 84 image. It's even lower resolution than I thought. If you have a grayscale interpretation of this thing, you would have 256 to the power of 84 times 84 possible screens, which is more than the number of atoms in the universe, I guess. So there's no way you can store this in a table. So we need to do something smarter. And that's what we can do with convolutional neural networks. So linear approximation of Q, that's what we just discussed. The state is this, because we decided that x and y are the state variables that matter. We create these linear models, one per action, and then we can use this first linear model and compute Q of going up for the current state, Q of going left for the current state, and we select the action based on the one that is the largest. Everybody understand this? What we're going to do now is a little bit more interesting. Instead of doing linear models like this, we're going to use a non-linear approximation of Q, which is what a neural network is. A neural network is a non-linear model. So the state is just going to be a matrix with the pixels in the current game screen, like this. We're going to input this image into a convolutional neural network, just like we studied last time. And can anyone guess what are the outputs of this network?
The actions?
The actions. What do you mean by the actions?
Reward of like next thing you can do.
The reward, it's close to that. What is it like here? In order to select the action, what information do you need? You need the Q values of each one of the possible actions for the current state. So here you are given the current state as input, and what you want the network to produce is the Q value of each one of the possible actions. So given that the game is in this current screen, if I execute one particular action up, what is the total score that I expect I can get? According to this neural net, which might be completely wrong, but we're going to update it. What is the total score that I can get if I execute an action left, given this state S, which is the screen, and so on. And then I can just compare them, then pick the best action. So that's the general idea of how we're going to use convolutional neural nets. Why are we using convolutional neural nets to do this instead of just a standard neural net?
Because the environment changes so much, and like how further ahead you get.
No.
Because we're working with the image.
Exactly, because the input to the network is an image. So every time that you have images or sounds, these convolutional neural nets, they learn these filters that make it easier for you to come up with the right outputs. So what kind of filters do you think a convolutional neural net would learn when processing game screens like this? In the problem of like classifying if something was a cat or not, the filters were like detect something that detects eyes or whiskers or legs or a tail.
I think it would detect game elements like walls you could crash into, enemy objects, bullets, things like that.
Yeah, exactly. That's exactly what these filters end up learning. There's like a filter that detects where the paddle is. There's a filter that detects if the ball is going to the right or to the left, that kind of stuff. And then based on this information, this higher level information that these filters learn, those things enter as inputs to a classic neural net that computes based on the weights of the neural net, the Q values. So like intuitively what's happening is that these filters, they are learning the state variables that matter for this game. Right? As I said, if we were hand designing a solution, we could, as human beings, say that, well, what matters is the X, Y of the paddle, the angle that the ball is moving to. We could design that by handcrafting these things. But those filters, they learn that automatically for us. So it really learns the state representation that is relevant so that you can compute these Q values correctly. Does that make sense? The intuition of why convolutional neural nets help. So this is the convolutional neural net. Just quickly remembering why they help. Again, like if you want to compute the probability of this being a cat, you can have like filters, like hand-designed filters to detect eyes. They come up with something like this. They tell you where in the original image an eye might be happening. But it's really difficult to know which filters are needed a priori for any like specific application, like face detection or playing Atari. So instead what we're going to do is we're going to come up with a convolutional neural net like this, just like we did last time. But now the filters that the thing is going to learn are not filters that help in a classification task. Because here, these filters, why was the network coming up with these specific filters? Because the task of the network was to classify whether there was a face in the image or not. So it learned that it was useful to know if there's a nose or if there are eyes or a mustache or something. And that's why those specific filters were discovered. When you're playing a game, the filters that are learning each one of the convolutional layers, they are going to detect game elements that might be helpful to the problem of predicting the Q values. Okay, so that's the difference. So up to this point, what we discussed was CNN for supervised learning, and now like image classification. Now we're going to do this for reinforcement learning, and then that's but where things become kind of not so clear how we're going to train this network, because the network should output the Q values of the different actions. Okay, so like in the Atari game, the image. This is exactly what happens in the Atari implementation of this thing. The image is a 210 pixel by 160 thing with a 128 colors, possible colors per pixel. those are the inputs to the network. Then there's a few convolutional layers, and at the end a classic neural net. And the outputs of this huge neural net are all possible actions that you could play in an Atari game. So you could just move the joystick up or right or right, so, and all combinations of that plus pressing the button or just pressing the button without moving the joystick. So I think there are 18, if I recall this correctly. So there's a lot of outputs. But the problem is, how do we train this? Because in supervised learning, like image classification, we could provide the network with a bunch of examples of this picture of a cat. You say the label, this is a cat, right? So you present labels of input and the correct output. If we want this network to produce the Q values, how would we train it? We would need something like, for this image one possible game screen, we would need to specify what is the Q value when of action up when you are in this game screen. You would also need to know in advance what is the Q value of going left if you are here, and going down and everything. So for many sample game screens, do we know these Q values to give this as training, as like the expected output in a supervised learning problem? We have no idea, right? The goal is we're actually trying to learn these Q values. We don't know that. So we can't train this. So what do we do? Just give up. Any idea how we can train this?
You can update it in a similar way that we did with linear regression.
Exactly. So what we're going to do is, initially the network is going to produce kind of random Q values. But every time that you take an action in a game, you still get all that information that we did get before that was really useful. You knew what the state was, you knew the action that you took, you got a reward, which is a feedback of how good that action was, and you observe what the next state is. So you get a lot of information about the outcome of your decision. And based on that, you can update your current guess for Q, which is going to be random at first, and come up with a new estimate that is a little bit less terrible than your initial one. And then you train the network to try to produce this new estimate that is a little bit less terrible. And that's what we're going to do. So more specifically, what we do by doing deep Q learning, so like Q learning is what I showed before, deep Q learning is just Q learning with a deep neural net. The way that this is going to work is like this. The agent observes the current state, so the screen of the game screen, and it inputs that into this network. The network starts with like random filters, random weights, and it outputs Q values for each one of the 18 possible actions, which are going to be completely off at first. So, and then based on these completely crazy Q values, you're going to pick the action that looks the best. Probably it's not going to be the best, but you execute it, you get a reward. Maybe you die, probably you die if you click at first. And you check what is the next state, the next screen of the game. And then we just plug that into this equation. Now the question is, how do we compute this thing? Well, the reward was given. We know what the reward is. How do we know what is the current Q of the current state and the action that you took? Where is this information coming from?
Well, we probably need to set some at random at first.
It's random at first, yes, but if I want to compute this quantity specifically, Q of the, so the state is the image, right, of the game, and the action is the action that I executed. How do you compute this number?
From the network?
The network, right? The network is giving us this. You input that state, that image here, and it outputs all the Q values. Well, what is the action that executes this? So you check what this number is. So you read out that output of the network, and that's the number that you plug in here. The reward you got, and then we have to compute this max. You do the same thing. How do you compute this max? S prime is the next screen of the game. And you need to know, you need to compare all possible actions and check which action has the highest Q in this next screen of the game. How do you compute this term? It's the same thing. You give as input to the network the image S prime. So S prime, like the next game screen comes in, it predicts all the Q values of all the possible actions in this next screen. So it's for all actions A prime, you get the Q values and you take the largest one. Right, so you show the next screen and you compare what is the best action in this next screen of the game. And that max out of these outputs, that's what goes into here. Does that make sense? So that's all the information that we get. This comes out of the network by giving as input the current image, and this is computed by presenting to the network the next image and comparing what would be the best action in the next screen image. Then you just compute this and you get your new estimate. So how do you, okay, so now you get a better estimate of Q, which you just computed based on your current outputs of the network. How do you update the network using backpropagation? What you do is, if you look at this equation, what's really happening is you have your current output of the network, which is this, but this is wrong. You want to update this. And you're updating this towards what quantity? You're updating this thing towards this quantity, right? That's why we had that alpha thing. It was like a little bit of the current output, but you want to move this value towards this thing. And how much you move, it depends on how you set alpha. What we're going to do is we're just going to tell the network that this is the value that should have been outputted instead of this. So let's say that I executed this action and it predicted Q value 5. But actually when you compute this, the value is 9.3. So what we're going to say to the network is 5 is wrong. You should have outputted 9.3. And then we just run backpropagation on that. That's deep Q learning, essentially. Does that sort of make sense what we're doing? Initially we're predicting random Q values. We use the Q learning equation to find out what is our best guess, like the new guess of what that Q should be, which is this. And then we just tell the network, well, the correct value is not that. That's what you produced, but the correct output is this. And then you just train the network based on that. Now there's one thing that we need to be careful about. Let's say I executed this action. So the output was 5, which is wrong. I computed here, it's 9.3. So I say this output actually is 9.3. What is the correct output that I should inform to the network for all the actions that were not executed? 0? No.
The same one that I got when you ran it first time?
Exactly. So if you show this image, the network is going to predict how good each one of the actions is. The actions that you did not execute, you're not going to update them because you have no idea if they're good or not. You didn't get any information about the actions that you did not execute. So if the network thinks that this is worth 1.5 and this is worth 2.3, you just tell the network, sure, 1.5 and 2.3 sound good. You just update the one that you actually got information from. So you're just changing the output of the action that you just actually executed.
Couldn't you maybe make an assumption that some of the other similar actions would also be stupid to make? Like if it's a game where you have a lot of lava in one area, and the action you did was go into the lava and you found out that that was a bad idea. The similar actions like going into the lava one step to the right is also a bad idea.
Yes.
So when you try to make an educated guess to adjust those actions too?
Yes, yeah, that's a really good idea, and it's some people do that. So for example, here the actions are going up and going up to the right. They are probably correlated, the Q values. They're not completely independent, right? So you're right that if you know, because you understand how the game works, but you executed this action, probably you can also update this one a little bit. Maybe update it a little bit less, but you're right that these Q values should be similar. So if you have that kind of information, you can include that as part of the training algorithm so that you update not only one entry, like one output, but many outputs, all the ones that are similar to the one that you actually execute. But this is basically what you do. That's deep Q learning. It's not. It's just a neural net. So again, if I was in some state S and executed A, I compute this quantity just like in the standard Q learning algorithm, and I, like say that was the action that I executed. I compute the new value based on the reward that I got and based on this thing, which is like the best Q for the next game screen. And then I set this Q of A, where A is the thing that I executed. That's not the correct value. This is what the network outputted. But I'm going to do one update of backpropagation by saying that this is what you produced, but you should have produced this. So there's an error, right? Like this was 5, this is 9. There's a 4 error, 4 points of error, and then you just run backpropagation based on that error.
Couldn't you like figure out that max for all of the actions and update them all at the same time, or is this just too long? Takes too long?
What do you mean? The max?
Yeah, I mean you do that step for like pretend you're taking all of the actions and see how it would result in the next step, and then update them all at the same time.
How would you do that when you're playing the game? You can only execute one action at a time in an actual game. Like this is running on a simulator of the game.
True. Couldn't you, I don't know.
So like depending on the setup.
Take the game back one step.
Yeah, if you have actual like if you have access to the simulator, you could say like run left and then reset the game one step back, take right, and you could that would make things super fast. But then you're not really playing the game. But yes, you could do that if you could go back in time. But anyway, the point is that you feed as input the current screen of the game. You get all these things, and only one of them is going to be updated. All the other ones you assume that they are going to remain the same because you did not execute those actions. You run backpropagation once, like one step of backpropagation. It's going to improve this weight. It's going to update the filters, and then you do that once again. That's the basic idea. So this is the complete algorithm. It's just what I described. Nothing more. Before I show you a few examples of this running on games, there are a few tweaks that the actual implementations of deep Q learning need to make in order for this to work efficiently, which I'm not going to discuss here, but it's easy to understand if you read the paper. One of them has to do with the problem of forgetting in neural nets. Does anyone know what that is? So let's say you have a training data of like students. So like you have the information about the student, age, and something else, and you have the grade that that student got in an exam. You want to predict the grade based on the age. Let's say you sort your data, your training set, like first, like younger people, older people, and then you give as input the first person, like some 5-year-old. Then you train the network. Then 6-year-old, train the network. When you get to like 9-year-old students, what is it that the network is really going to be learning at that point? It's because you're updating things sort of in order, the network is going to be really good at predicting older people, not younger people, because younger people were like the examples that you presented 100 years ago, like at the beginning of the training, but all those updates were sort of undone because you presented older students afterwards. So what could happen here? Does everybody understand that? So the network sort of always tends to be updated to become better at the last examples that you showed. So what could happen here if you're playing a game? How would that manifest itself on a game playing network? Again, you show like one possible situation of the game, you update that, you go to another screen of the game, you update it, and you run this for like 1 million situations in the game.
It make you keep playing like the late game, but only if you get past the early game.
Exactly.
Like in the end, start dying in the early game.
That's right. So if you already played like 100 levels, and you're updating this in order, the network is going to focus like its updates so that it becomes better at the latest things that happen in the game. But when it executes that update, maybe it's going to forget how to play in the earlier levels. because you're not updating those things. So there's a trick